So, continuing our discussion about permutation ellipses. What are permutation ellipses? They were defined in this paper by Kimberling and Moses. Basically, what you do is you take a triangle ABC, you elect a point on its plane whose barycentric coordinates are P, Q, and R, and then you permute those barycentric coordinates. You get 5 new points, and what they show in this paper is that these 5 points, along with the original one, so 6 points, lie on the same permutation ellipse, and the center of this ellipse is G, and the major axis of this ellipse is fixed. So no matter where P is placed, you're always going to get a major axis that goes through line X2, X1341. Okay, so it's a pretty recondite triangle center in Kimberling's list. In fact, I believe I opened it here. There it is. X1341 is the X-simile center between the circumcircle and the Brocard circle. Now, I want to show you guys this very cool phenomenon, which is the following. If you take X2 and X1341, fixed axis, right? And you make P right on that axis, the 5 permutations, barycentric permutations of P, are going to each ride on a straight line. So you can see here. So if I move this triangle C around, okay, I'm going to get a different family of permutation ellipses. But once you fix your ABC, you got your line X2, X1341, so this line here. And then if you just make this experiment, let's make my ellipse pass my P right on that very line. So we get this really cool degenerate phenomenon where all the permutations now are going to be on lines that converge to X2, or pass through X2. Okay, now there's a really cool thing. If C is such, okay, so if you fix AB and I move C, there is a one-dimensional locus of C such that X3, the circumcenter, is going to be on that line. So let's manually find one of those triangles right here. For example, this one over here. Now, whenever this is the case, 2 pairs of lines collapse to the same line. You can see here that they're almost doubled up. Okay, so you have this. These used to be, so if I perturb a bit, these used to be 2 lines. These used to be 2 lines. And P2 did not lie on that line. But when the triangle is such that X3 lies on X2, X1341, you get that P2, first of all, will coincide with P. This is the first phenomenon. So there's one of the permutations coincides with P itself, and the other 2 pairs of permutations coincide with each other, and they will ride on doubled up lines. Okay? So here C is not exactly at the position, but there's going to be a one-dimensional locus for C. Okay? Now let's observe a similar phenomenon, but in what we had done in the previous video. And what was that? In the previous video, we had P not riding on that special line, but riding on a circumcircle. And what we saw in the previous video was that when P rode on the circumcircle, each one of the permutations on the magenta conic swept a circumellipse. It turns out that if C is such that X3 lies on that special line, okay, so let's go ahead and manually do that. The same thing that we saw before happens. Pairs of circumellipses double up, and one of the circumellipses becomes the circumcircle. Okay, so if I'm going to perturb C a little bit here, okay, you can see here that is if you keep your eye, if you watch X3, I'm making C be such that X3 is going to lie on that special axis line there. When that happens, you get this doubling up phenomenon. So a couple of questions here. What's the locus of C for both this example and the previous example with the lines, right? What's the locus of C such that X3 is on that line? Is that a cubic? What kind of a locus is that, assuming A and B are fixed. Okay. The second question is when you're there, in this first case here, what is the angle? Is this a straight? Is this a 90-degree angle or not? I don't know. I can't really eyeball it. Let's go ahead and take this to a more extreme value here, so it doesn't look like. So yeah. So for example, over here. Yeah. So this is clearly not a right angle thing when there's a doubling up in this case. So this case is the one that I saw. I mentioned before. P is riding on that axis, right? So you got the straight line phenomenon. P is riding on that axis. So you can see here that these two doubled up lines do not intersect in general at 90-degree angles. But you know, the same question I had before was what's the locus of C such that x3 lies on the line x2 to x1341 when you get this doubling up phenomenon? Is there anything interesting here? And the second case, more complicated case with the 5 ellipses, one question we can ask here is when there's doubling up, are there any interesting properties? Looks like there's going to be some symmetry, right? So for example, this pair of ellipses and this pair of ellipses, they look symmetric. Okay, so there might be something about their foci or you know, their isogonal preimages, which are lines. But it looks like these are pretty cool. So you know what you can ask here is, as C moves along this locus that keeps x3 on the line, what's the locus of the foci of this ellipse? Okay, all right. So in the next video, I'm gonna talk about further phenomena involving the homothetic family, the Poncelet homothetic family, as it relates to this geometry. See you in the next video.